full screen now? Perfect. All right. Cool. So hello, everyone. My name is Marcus. I'm the co-founder and CTO at Neutron Star Systems. We're a space startup based out of Cologne in Germany. We also have an office in the UK and just incorporated an office in Colorado Springs in the USA, following our participation at the Catalyst Accelerator. So today, what I'm going to tell you about is how high-temperature superconductors can act as an enabling technology for Mars missions. So high-temperature superconductors are our core focus as a company, and what we do is we apply them to spacecraft systems. So I'll sort of give an introduction on why we need to consider them, and I'm going to do this from a point of view of power and propulsion, because in order to really understand the benefit of the superconductor, you need to look at their applications and how they affect all sort of parts of a spacecraft. So in order to sort of get you all up to speed, I'll start with this, what we call this non-dimensional Sikorsky equation, which is the baseline of the whole study which we performed here. I'll introduce exactly what high-temperature superconductors are and why they're useful for space, and sort of explain how they're an enabling technology by looking at their impact on mass fraction optimization, which is ultimately the goal of pretty much any space mission. So to start with, we're going to start on the topic of in-space propulsion. So when you have a given orbital transfer with a given delta V, the classic rocket equation will tell you that if you want to maximize the amount of payload and minimize the amount of fuel you need, you want to always go with the highest specific impulse. Now, if you're looking at chemical propulsion, this is pretty much true, because with the highest specific impulse, the way the chemical engines work, they just take their energy directly from the fuel. So if you can maximize the ISP, then you can maximize the amount of payload and minimize the amount of fuel. With electric systems, it's a little bit more difficult, and this is because they're low thrust systems which get their energy from the electrical power system on board, not from the fuel itself. And that means you need to look at this equation a little bit differently. And in order to do that, you first need to understand the fundamental trade-off of all electric systems, which is shown on this chart. On the y-axis, we have thrust, and on the x-axis, we have specific impulse. So in general, if you're going to go to a high specific impulse operation with an electric system, then you need to, you're going to trade off against your thrust. So your thrust is going to go down. Now, this is really important when we consider any mission with the transfer time, because we're going to need a certain thrust requirement in order to fulfill that transfer time. If the thrust is too low, it's going to take us too long. Now, what you'll notice on the y-axis is not just thrust, but thrust per power. So if we want to go to a higher ISP, we can still achieve the needed thrust, but we need higher power to do it. However, this actually means that we need a heavier power system, because we need more solar arrays, we need more cabling, we need more electronics. So actually this in turn also needs to be considered when you look at the overall mass fraction of the spacecraft. Essentially what I'm trying to get at with this chart is that we also need to consider the power system mass when we look at any electric propulsion orbital transfers. And this can be done with this equation. I'm not going to go into too much detail on how it's derived, because this would take several hours. But essentially, it tells you for a given orbital transfer, what is the payload mass fraction, depending on a number of different parameters, including the orbital transfer delta V, the time limitation of the transfer, how heavy your power supply is, and also the characteristics of the propulsion system in terms of exhaust velocity and thrust efficiency. The exhaust velocity is proportional to the specific impulse. So what we can do with this equation is actually plot for a given set of parameters and a given mission scenario, what is the difference in mass fraction that we get with ISP. And it's not actually just always increasing. You actually end up with curves which look like this. There is actually an optimum specific impulse, which if you actually go too high, your payload mass fraction ends up becoming lower. And this is because the fuel saving that you have with the higher specific impulse is negated by the extra mass of the power system that you need in order to perform at the high thrust that you need for a given transfer time. So what you see on this chart is for the case of a orbit raising of geocommunication satellite from GTO, geostationary transfer orbit, to GEO. And this is plotted for a number of different time constraints. The industry standard for all electric propulsion systems on all GEO satellites is for 6 months orbit raising. So you see there the optimum ISP is about 1,600 seconds, give or take. And this explains why Hall effect thrusters are very popular at the moment for geosatellites. So this is a little bit of the background of what we're sort of starting to look at. The important parameters here are the mass-specific power of the power supply system. If we can reduce this and make the power supply more mass efficient, then we can start to access higher payload mass fractions. This is where high temperature superconductors come in. So a superconductor is a material which can conduct electricity with zero electrical resistance. And this opens up a lot of new possibilities, such as the ability to conduct huge amounts of current in very small, lightweight tapes. Also to generate strong magnetic fields on the order of Teslas, which would not be possible with conventional technologies. And high temperature superconductors refers to a specific subset of superconductors which were discovered in the 1980s, and they have a critical temperature above 80 Kelvin, which is the boiling point of liquid nitrogen. And this is important because you can make them superconducting at relatively high temperature, which means the cryogenic demands are somewhat reduced. That makes them now more suitable for space applications. The other key advancement that's happened with these materials in the last 20 years is that they're now available as commercially mature products made of multi-layer materials. You can buy these tapes, superconducting tapes, basically off the shelf from suppliers all around the world. So they're available at very reasonable prices, at economies of scale, and together with their high temperature characteristics, they're now well suited to be used in space applications. As I mentioned, they've achieved economies of scale. This is thanks to a very modular production process, which takes advantage of very scalable manufacturing processes. And as a result, we've been able to achieve very high yields, high quality standards, and the economies of scale allowing us to produce these at relatively low costs. So all of this makes them suitable for use in space, where they have actually a number of applications, which I'll go into in some more detail. I think these slides will be made available, so everyone can take a look at some of the applications on this chart in their own time. But I will go into some specific ones which are of special interest. The first is for re-entry shielding systems. The concept here is to use a superconducting coil to generate a magnetic field which can shield spacecraft as they re-enter a planet's atmosphere. For example, this can be used on Mars missions because, of course, any probe or rover or lander needs to go through the Martian atmosphere. And this part of the mission is one of the most dangerous parts. Firstly, it generates a huge amount of heat, which is imposed on the spacecraft surface. And this usually requires things like aerobrakes, aeroshells, or thermal management systems, which can weigh or which can take up as much as 35% of the vehicle mass. So this is a huge weight issue that we have at the moment. The other issue is that the plasma that forms around the spacecraft during re-entry also blocks any radio communication. So you can't communicate with the capsule during landing. If there's a problem, you can't use it to transmit scientific data. You can't speak to astronauts, for example. The approach with superconductors, in theory, will solve both of these problems. Firstly, by deflecting the plasma layer away from the spacecraft and significantly reducing the heat. And secondly, this deflection will also open a magnetic window, which we can use to communicate with the spacecraft. In fact, we already have a research grant from the European Union, which is investigating this project. We are one of the consortium partners, along with 9 other universities and SMEs in Europe. And in this project, we will be building a superconducting magnet demonstrator, which will be tested in a plasma wind tunnel, which simulates the re-entry conditions. Another application we can use the superconductors for is actually for cosmic radiation shielding. By similar means to the re-entry shielding, we generate a strong magnetic field which can deflect and protect against space radiation. So this kind of application will also be suited for a Mars mission where the crew may need to be in transit for up to several months and will need protection from the harsh radiation environment. One key application that we're looking at for the superconductors is on applied field magnetoplasma dynamic thrusters. This is a type of electric propulsion. I'll just give you a quick intro on the tech. It's formed of 2 electrodes, which are insulated from each other and between which we feed an electrical discharge. Here we end up with an electric field across the electrodes, and we feed a propellant between the 2, and in this electric field, the propellant becomes ionized. There's now a electrical current running through the propellant, through the plasma, between the electrodes, which induces a self-induced magnetic field, resulting in an electromagnetic acceleration of the propellant. And this is your basic magnetoplasma dynamic thruster. With the applied field version, we enhance this by adding an external coil, an electromagnetic coil. This generates a further magnetic field, which leads to two more acceleration mechanisms known as the Hall and swirl acceleration. And altogether, these form the applied field MPD thruster. This has a lot of benefits over the existing propulsion technologies. Firstly, because we're accelerating the plasma in a very wide volume, it's very scalable. We can put huge amounts of power into this whilst keeping it relatively lightweight and compact. It can also operate on several different propellants, which means we don't need to depend on xenon, which is extremely expensive. And it can also be throttled over a wide range of operation. So this is the kind of thruster technology which is needed if you want to start moving larger vehicles to Mars because of the large delta V involved. We have a prototype in the University of Stuttgart. That's our main scientific partner. This is a 100 kilowatt class, so very high power. And for this power, it weighs only 13 kilograms, which is extremely light and extremely compact. The issue is that at the moment, this is using a copper electromagnet, which weighs much more than that, 150 kilos. It consumes nearly 300 kilowatts of power. So clearly, this is the main issue that is preventing it from being flight feasible. Nonetheless, with this prototype, several great results have been achieved with thrust efficiency up to 62%. This is on par with the existing electric systems on the market. And what I want to point out with this slide is the influence of the magnetic field. So if we're able to increase the magnetic field strength of the external coil, we get significant increases in efficiency. We're able to operate at lower current and higher voltage, which is very beneficial for the thruster lifetime. And most importantly, we're able to get to high specific impulse and high thrust. So when you put all this together, you see that in order to make this very high potential technology flight feasible, we need a strong magnetic field, and we need something which is lightweight and low power consumption for the coil. And this is exactly where the superconductor comes in. And this is the supreme concept which we are currently developing. One of the use cases is for Mars missions. It's formed of 5 main subsystems. The applied field module is the one which contains the superconducting coil, and that's where we're really having the main impact. So by using the superconductor instead of the conventional technology, we're able to reduce the mass of the magnet by a factor of 4. We reduce the power consumption by a factor of 300 and can enable the magnetic field strength increases up to 4 times as strong, which means we'll be able to achieve really high performances and long lifetimes. So if I come back now to this chart, which I showed at the start, what I've added here is a label to show the 2 sort of current legacy propulsion technologies that are flown in space, the Hall effect thrusters and the gridiron thrusters. In both cases, they have a fairly narrow operating range confined to just a few hundreds of ISP. With Supreme, we expect to be able to access this entire blue shaded area, also thanks to the various propellants that we can utilize. And that means that we can operate at the optimum ISP that is needed for the various mission scenarios that we look at. So bringing everything I've told you together, what we did on this study was we took a few mission scenarios and we looked at, these are from literature where they worked out the entire mass of the various power systems, the propulsion systems, and looked at basically different mission scenarios, how much time and how much propellant we're going to need to get to these locations. So we have a Mars cargo mission as well as 2 other examples. And what we did as a study is we evaluated how much mass can we save using a superconducting system, how much can we reduce the mass specific weight, and how much can we improve the efficiency of the propulsion system using this technology. And we then plotted the results of this mass fraction optimization equation for a number of different transfer time limitations. This is what we ended up with. So what you see here is a comparison for Mars cargo mission of different time constraints and different power architectures. The dotted lines are considering the conventional power and propulsion technologies, whereas the single line is for the superconductor-based versions. And as you can see with the single lines, we're able to achieve much higher payload mass fractions, in the best case with increases of as much as 7% in payload mass fraction. And we're able to operate at a higher specific impulse as well, which means that we can bring more payload to Mars, we can have actually a bit more flexibility on the different types of orbital transfers that we do. And essentially, this shows that this can act as a significant enabling technology for these high power missions, especially for locations such as Mars. So to wrap up the main takeaways of the talk, firstly, if we're going to consider high power missions, which we need to consider for advanced concepts like Mars cargo, interplanetary crew trips, and even Mars servicing activities, then we need to also look at the mass of the power system as a key part of the trade-off study. With superconductors, we have a technology which fits perfectly for space because they are extremely low mass, they're very compact, and they have 100% efficiency. And these are all parameters which are critical for any space systems design. In particular, using them for applied field MPD thrusters has a lot of advantages because it enables them to be flown in a very compact and lightweight form, whilst also offering alternative propellants, high efficiency, and throttleable operation. And in fact, with using superconductors throughout the spacecraft, not just for the propulsion system, but also for radiation shielding or for power management and distribution systems, we can significantly increase the amount of payload mass fraction that is deliverable. With all of this in mind, I think it's quite safe to say that use of superconductors can act as an important enabling technology for future missions, especially for cases like going to the moon, going to Mars, and eventually for new scenarios like asteroid mining. So thank you all for your attention. We're happy now to take any questions, and if anyone wants to get in touch and learn a bit more about superconductors and what we're doing in the space industry, then please feel free to contact me below.
Yes, thank you.
I imagine everyone here probably has some interesting questions to ask. I have this is very exciting technology.
Is actually getting involved and turning that into something more.
I'm sorry. Oh, was David trying to ask a question? Oh. Anyway, I'll just ask if based on some recent results from the Spark project, the Commonwealth fusion technology, they were able to use. It sounds like a very similar high temperature superconductor as you to achieve a 20 Tesla magnetic field strength.
Correct.
Which I had no idea we were that close to that level of magnetic field in anything like this application. So yeah, I guess the future is now. What do you think your predictions are as far as your upper limit for your thrusters of magnetic field strength, and what do you think the results of that will be? Is that your 8,000 ISP hydrogen fuel source number?
Yeah, so we plan, well, essentially no one knows how far it makes sense to take the magnetic field. All the scaling models from the wealth of data that has been performed with many MPD prototypes all over the world agree with the fact that with the high magnetic field, we get higher efficiency. So far, 600 millitesla, I believe, is the max that has been tested, although research in China and Russia are now also looking at higher magnetic fields, also with superconductors. So what we aim to do is to see how high we can take the efficiency, because there will be a peak beyond which it doesn't make sense to increase anymore. Our current estimation with our models is that this will occur somewhere between 1 and 1.5 Tesla. The magnets from Commonwealth, I also saw this story and it's very exciting. You know, you need 20 Tesla for things like fusion. Fortunately, we don't need such a high strength, which means we can use relatively smaller coils than they do. But that's exactly another example where these superconductors have already seen a lot of maturity on Earth, because they're also used in all the major fusion reactors on Earth. And I know there's a lot of interest at the moment in the potential of nuclear fusion as a spacecraft power source. And if we're able to do that, then it's another synergistic use of superconductors where we'd have it again for the power management systems, for the power source and the propulsion. So yeah, to summarize, we're looking at 1.5 Tesla, a maximum of maybe 75% thrust efficiency, and like you said, with hydrogen up in that 8,000 to 10,000 seconds ISP range.
Thanks. no one else has any other questions, I have another one, but I don't want to hog your time.
Please.
Okay, I'll go ahead then. You're obviously some very near-term thrust concepts. One of the longer-term sort of wild interstellar, interplanetary deep space mission concepts is to use a magnetic sail, and that only really is enabled through high temperature superconduction, giant wire reels spun out from the craft. What do you think that with the current family of high temperature superconduction is even worth considering, or are we still generations of higher temperature needed before that's feasible?
I'm not too familiar with the magnetic sail concept. I'm not sure if it's similar to solar sail, but in reality, unless you have ridiculous amount of currents, and I'm talking, I'm talking beyond kiloamps level, then the superconductors that we have today will be more than capable of doing that. So the standard tapes that you buy from suppliers are 12 millimeters wide and less than a millimeter thick. And even with that tape, you can conduct 500 amps of current. So you consider you can use wider tapes, or you can use a multiple number of tapes to get to that kiloamp number very easily. And as for the cooling at 70 Kelvin, this is also not really too much of a challenge these days with some space qualified systems available. So I would be very surprised if the superconductors can't be used for that application. But it is something I'd like to look into, because I'm always looking for new use cases.
Yeah, the magnetic sail case is essentially using the cosmic radiation, or no, more so the solar radiation, and basically creating a magnetic field that deflects it, and using it just like solar wind, except with a high strength magnetic field, you can get essentially a larger total mass of propulsion. So I'm sure there are other people on the call who understand that concept way better than I do, but I just know that it would only exist in the presence of a major superconducting coil being spooled out. So,
do you know what kind of field strengths they talk about there?
I don't. It's a very much a sci-fi kind of concept. I've never seen anything that tried to elaborate on it. I'm sure other folks in here would know more than I do, though.
Well, I think a couple of years ago, some people might call the magnetic shielding for re-entry sci-fi, but now we're doing it. So
absolutely, the future is now. I didn't realize we were already here.
So it's really impressive work, Marcus. Remember meeting you 2 years ago, one evening during ISC 2019 in DC.
Yeah. I was just there this week for the conference again.
Nice.
Yeah, things are good.
One question I had: if humans in biology would be within this superconducting magnetic field, what would be the effects, if any, that these high magnetic fields would have on the humans in biology?
So we don't really expect anything bad. I mean, you have to remember the same superconductors are used already in MRI machines for healthcare. So people go in there all the time, and as long as you're not wearing your pacemaker or your watch, then you're generally going to be okay. In any case, with the superconductors, thanks to the lightness and the flexibility of these tapes, we have a huge design space, and we can really actually create new field topologies which aren't possible with the traditional conventional materials. So if there was a need to somehow have regions of low field where the humans need to inhabit, if it turned out that did become a problem, then I think we could design in a way that we can still fulfill the use of the superconductors but have it safe for the crew as well.
Thanks.
Okay, Marcus, I have a question. I'm Bruce McKenzie, one of the founders of MarsU. There's another application for electric thrusters, which is station keeping. And in that case, it doesn't matter how heavy the power supply is. So if you have a very heavy power supply, it takes longer for your orbit to decay, and then it's extra thrust needed to bring it back. But it ends up, not being dependent on the mass of the power supply. And you might actually have surplus power if some other, motors that, experiments are not currently turned off. Do you think it would be feasible to have the 8,000 to 10,000 seconds of ISP? And a related question, could you design a thruster that can run on a variety of materials? So let's say we have we've collected space debris, and we have a mixture of aluminum and plastic and maybe some carbon dioxides that people have exhaled. Could you run aluminum, carbon, oxygen, and hydrogen all into the same thruster as propellant? Thank you.
Yeah, so regarding your first question, so the stuff I presented today was for these orbital transfers where we have a transfer time requirement. So station keeping, of course, there is no requirement, and you're right. This is actually the case with many satellites today, especially the geosats. They use all of their power for the thrusters for the orbit raise. And then once they're up there, they run the thrusters in a lower power mode because they don't need the same amount of thrust for the station keeping, and the rest of the power is used for the communications payload and for the other subsystems. So whilst we may have an excess, there's always other things you can do with it. You can increase data rates. You can use that for onboard processing, spacecraft autonomy. I mean, we've got a lot of ideas. So in our eyes, too much power is never a bad thing. The second question about the ISPs, yeah. So I mean, the ISP will depend on the propellant you use. So something like hydrogen, you get the highest ones. Things like nitrogen is going to be a little bit lower, but in turn you'll get higher thrust. You can run the thrust on mixtures of things. You can't run it on anything. So anything which ends up producing atomic oxygen is a no-no, because that will destroy the inside of the thruster.
So
oxygen,
you don't want to run it on CO2.
No, we don't want it running on CO2. We can run on metals. There's been a lot of data gathered on things like lithium and magnesium. I believe there was also some data gathered on aluminium, but I need to double check this. The issue with metals is that from a performance point of view, they're great, but from a practical point of view, they're not so good because they get deposited on spacecraft surfaces. I mean, the lithium especially, it goes everywhere. So if we can avoid to run on that, we would prefer not to. Our favorites are noble gases like argon and nitrogen or hydrogen-based compounds like ammonia, LMP103S, and so on.
Okay, thank you.
Thanks, Bruce.
Wonderful. Alrighty. It's like Marcus, is our last presentation. We'll go ahead and jump on to the next part for the next 10 to 15 minutes. Send some slides here. Okay. So for the reviewing and award process, just a reminder here that so there are 6 final presentations that we heard from, and now we're going to have a live democratic vote with an online survey. And so when we're voting, we should keep in mind that our votes should be based on these 5 factors and each of our prior knowledge and research and experience to evaluate these 6 presentations. And here they are as a reminder.
Hey guys, this is Terry Cole.
Yes.
Really, I don't know if I should be included in this. because I seem to be the only PhD student here. And I mean, I appreciate the audience and everything, and I've really enjoyed the time, but I don't know if I really should be included in this group. And I do appreciate the gesture.
Okay. All right, well, we can
What do you guys think?
exclude you from the survey, I guess, then
Okay.
that would work. But yes, we understand. Let's see. Just updating the survey, and I'll send it your way.
If anybody wants to chime in with a question or comment, well, Cole is doing that, feel free to.
Yes.
And feel free to switch to gallery view and wave.
I will jump on board. One of the things as a designer that are critical is to bring multidisciplinary ideas into the designs. And it was fascinating to me to see different topics that are apparently unrelated. And they gave me a lot of new ideas. So in that sense, I really appreciate the contributions that everyone had, because the only way that I can see that we can actually generate livable spaces on Mars is by bringing multidisciplinary approach. So it was very, very appreciated. And thank you, everyone.
Yes, well said, Alfredo. I would echo what you just said. Yes, and so here's the link to the voting form. We can take up to three or so minutes of your time to vote with this short survey here. It's an anonymous voting form, and each of us can vote once. So.
And let me summarize. We're voting on the criteria of the need, the benefit to society, novelty, design and feasibility, potential impact to sustain life and humans on the Martian surface.
If Marcus Collier is still on the call here, I have a follow-up question about power sources.
Answer.
So I know you said that no, too much power is never going to be a problem, but have you considered design? How does the system manage starts and stops, you think, so that you could use a high power source for short bursts of time as opposed to having extended thrust? So in other words, could we optimize a smaller power source, sort of like the 100 kW size power source, and enough of a battery pack that you could do 8-hour thrusts and then recharge, etc.?
Yeah, I mean, what I'm presenting here is not a whole new class separate from electric propulsion. I mean, this is still something which you would like to fire. Ideally, you can fire it for days or months at a time. 8 hours is also not going to be a problem because the startup cycle is on the order of less than a minute. So it's really the kind of thing where the simplest option will be to have it continuously running over longer periods than have it running on short periods, because even if you sort of try and do it in a burst, you're not going to be really generating any more thrust, or you might be able to, but it would be not good for the lifetime because you'd have to run it in a very sort of high intensity mode. So I mean, if it was up to me, I'd just run it steady state for a longer period of time. and you'll achieve the same goal, but more efficiently.
This is Terry. One quick question. The availability of doing such on terrestrially, I don't remember how, is that possible? If so, how?
I didn't quite understand the availability of doing what terrestrially.
If we can generate the same power using the same method terrestrially.
Well, yeah, I mean, so in the picture behind me, this is a 100 kilowatt class thruster, which is in the University of Stuttgart, and they've also tested megawatt class thrusters. So the terrestrial power generation is not really an issue. You just need a large enough facility from the vacuum point of view. We have a couple in Germany. There's many in the United States. For example, the one in University of Michigan. That's where they're developing the X3 thruster, which is also 100 kilowatt class. And NASA has also got a high power facility. So you just need a large enough vacuum chamber, the right sort of materials at the end, and some facilities also have water cooling systems to help with that if needed.
Terry, is the question what you were asking? Is it that are we approaching a place where this thruster could actually be used for like liftoff? You know, is the thrust to weight ratio going to get anywhere near that
well,
place?
I don't think it could because the ISP, but I'm really looking forward for is whether or not it could be used for power generation as a green kind of thing. One of the big pushes, you know, there's a lot of reasons to go to Mars and to go to space. But one of the big reasons that I feel is so that we can quote unquote re-green the earth. So we got to get manufacturing. We got to get these industries that would have benefit more in space. Well, if we, of course, we have solar, wind, you know, all the renewables. But is this something that could replace a nuclear coal plant or a coal plant or something eventually?
I mean, the superconductors themselves are not a source. They're the means to transmit. They're also the enablers for something like fusion. Like I said, all of the fusion projects, they use the superconductors because you need the high magnetic fields there. Superconductors have already been used for power transmission lines and power grids. There was a recent project in Munich where they have a few kilometers of superconducting cable. They can also be used in wind turbine generators or other power generators. So again, there's been prototypes of those built, which are significantly more efficient because the losses are reduced. You can also use them for things like transformers, electrical substations, and the other applications we see are on marine and aviation. In aviation in particular, all electric aircraft with superconductors is a major component of most of the roadmaps of the major manufacturers. Airbus just launched a project for a 500 kilowatt aviation powertrain using superconductors. So if you want to go to all electric and reduce emissions there, the power density and the mass that they can achieve is by far the most competitive option than using conventional cabling.
Just one more question about that. In space is no problem because we're 700 degrees negative up there, but here on space or here on Earth, for this to work, doesn't it need to be super cooled?
They need to be cooled in space as well.
Okay.
I mean, again, with the thruster, this plasma plume can make the inside of the thruster as much as 2000 Kelvin. These things need to be cooled down to on the order of 60, 70 Kelvin. Having said that, that is a completely different beast compared to traditional superconductors, which have to go down to 4 Kelvin. So your cooling systems need much less power. They can be much smaller, much more compact. And for the kind of cooling loads that we expect, we already have space qualified cryocooler solutions, which will weigh on the order of 10 to 15 kilos and power consumption of a couple hundred watts. So when you're talking about thruster power classes of 5 kilowatts and above, then it makes sense. We've done that trade-off.
Fine. Well,
Yeah, and let me point out that to cool a high temperature superconductor, you can use liquid nitrogen, sort of like a buffer. So you generate liquid nitrogen whenever you have surplus power, and then that'll keep it cold as long as the nitrogen is not yet boiled off.
In some cases, you can also cool them with conduction cooling. So you don't even need a fluid. You just you have your cold end of your cryocooler, and just through conduction, it keeps the rest of the coil cool. We have a lot of options.